Hi there, I'm Darcy. I'm a software engineer here at Google, and I work in Google Cloud. My coworker, Ray, and I are going to talk about the problem divisible divisions from CodeGem 2021's Virtual World Finals.
Hey, I'm Ray, a software engineer at Google, and I work on the YouTube ad serving site reliability engineering team. We both have experience as coding competitions contestant, so it's really nice to be now on the other side of the table.
Let's start out by looking at what the problem is asking for. We are given an initial sequence of digits and a second integer, which we'll call the divisor. Our goal is to count how many ways we can split up our sequence of digits so that a lot of those chunks are divisible by our divisor. In particular, for every pair of back-to-back chunks, we need at least one of them to be divisible by our divisor.
That's right. So let's consider some of the ways to split the first few digits of pi and a divisor of 5. Some of those are good, some of those are bad, and we have to count the good ones. Bad splitting is one where there is at least one pair of back-to-back numbers that are not divisible by the divisor. Everything else is a good splitting.
Now, let's explore how we can use dynamic programming, or DP, to solve this problem. Let's say the original sequence is 145217. For each prefix, let's compute all of the good splittings. So in this case, we're going to have 6 prefixes to consider, and if our divisor is 7, then these are all the valid splittings for each of the prefixes except the final one, which is the entire string. We're going to work together to try and fill in that final column.
All right, that sounds great. I think the first step should be to break each column into 2 groups. The splittings that end in something divisible by 7 in this case, and those that don't. Now let's fill the last column. Notice that all valid sequences in the last column must be one of the other sequences we have already found, plus one more number added to the end.
That is a great observation, Ray. Let's consider all the possible numbers we could append to the end of these to get a valid sequence. First of all, the last number could just be the 7 at the end of our sequence. In this case, 7 is a multiple of 7, and so we can append it onto any valid sequence from the previous column. Next, let's consider 17. This is not a multiple of 7, so we can only append it to valid sequences in the 1452 column that ends in a number that is a multiple of 7. Otherwise, we're going to have 2 numbers that are back-to-back that are both not multiples of 7. In this case, though, there are none to append it to.
Exactly. We can continue now with 217, which is a multiple of 7. So we can append it to anything in the 145 column. Next, 5217 is not a multiple of 7, so we can only append it to sequences that end in a multiple of 7. In this case, there's only one sequence. And we have to remember to put it in the bottom row of our DP, since the last number is not a multiple of 7. Next, we have 45217, which is not a multiple of 7, so we have to append it to something from top row of our DP, which there are none of again.
Right. And finally, we have to remember to consider the full number itself. This is not a multiple of 7, so we include it in the bottom part of our table. At this point, we've handled all possible final values of our sequences, and we see that there are a total of 8 valid sequences for this column. And since this column represents the entire input sequence, this is the answer to the question. Now, of course, we don't actually need to remember the exact sequences like we have here. We just need to remember the count of how many sequences are in each cell.
Right. Now the thing is, computing this will take quadratic time if we compute the suffixes on the fly. That is good enough for TextEd 1, but it's way too slow for the bigger cases in TextEd 2. To tackle those, we will build on the ideas that we just discussed in our dynamic programming solution. When we want to find the 217 suffix here, that'll be the whole number, subtracting some prefix that is multiplied by the power of 10. If 217 is a multiple of 7, then the numbers we are subtracting must be the same mod 7.
Right. And in general, we're always interested in some prefix a minus some other prefix b. This difference is a multiple of n if and only if a and b are equal to one another, mod n. We can use this to speed up our dynamic programming solution from before. Now we're not going to go into full details here, we're just going to give a few hints to help you put it all together. So, if we know the current value of our prefix, modulo our divisor, as well as the mod of all other prefixes before us, multiplied by some appropriate power of 10, we can then determine which of our numbers are divisible by 7, simply by looking through the list for any prefix that has the same modulus as us, which is 2 in this case. It will help a lot to now bucket all of these prefixes that have the same modulus together. And then, when we're moving from one prefix to the one immediately after it, note that we need to multiply all of our prefixes by 10, which sort of shuffles these buckets around. We're going to need to create a data structure that can keep track of all of that shuffling efficiently.
That's right, Jersey, but bad thing is that's not all. Another thing we have to consider is whether the given integer is relatively prime with 10 or not. Here's a hint on that. When they are relatively prime, all modular inverse operations are straightforward. You don't need to do anything fancy on that. But when they are not, we need to focus on how many 2's and 5 the divisor's prime decomposition has. We'll need to use this hint to split the problem into small and large substreams. Then use that magic data structure that can multiply all the prefixes by 10 quickly to solve the problem. There are quite a few small details we have left out, so make sure you check out the full problem analysis on g.co/codegen.
Wow, I thought the test set 1 solution was already pretty tricky. It's amazing that we need all of those extra insights to solve this, and that the finalists have to come up with all of this in such a short period of time.
I know, it really is incredible. But well, that's all for now. Thanks for watching, and we'll see you at the next year's CodeGen.
Bye.